Hello everyone, my name is Zhou Rongzi. This is my topic. This project contains two parts. For the first part, I will develop a Python script to automate the generation and rendering of recursive 3D objects and use it to make a real-time interactive Mandelbulb fractal in Blender. For the second part, I will implement the Metropolis Markov chain Monte Carlo method to sample 1D, 2D, and 3D arbitrary functions, and thus make an integration of a Gaussian integral. For part 1, let me introduce some terms first. What is Mandelbulb fractal? Fractal is a kind of patterns that its type of shape yields or elaborate details forever, no matter how far you zoom into it. This concept appeared quite early, but due to the incredible complexity to fully capture its shape, it didn't enter the public's view until March 1, 1980, when Mandelbrot rendered his equation with a powerful computer and left us with this impressive picture. However, contrary to its incredibly complex patterns, the equation is elegant and simple, which is merely z equals to z squared plus c, where z and c are complex numbers. Mandelbulb is the three-dimensional version of Mandelbrot fractal, which was first constructed by Daniel White and Paul using spherical coordinate in 2009. For the three-dimensional fractal, its coordinates is given by these three equations. Blender is a free and open-source 3D computer graphic software able to create 3D printed models, interactive 3D applications, animated films, and even computer games. Its enormous simulation features make it a great place to turn any interesting math into something more tangible. However, as a professional graphic software, it is not so user-friendly, especially for beginners to operate with all kinds of tools by a mouse and a keyboard. Thankfully, a feature called Node Editor can help us do anything from modeling to texturing, which is kind of visual and elemental programming. However, as you can observe in the following parts, the process of adding nodes to implement mathematics is too tedious, especially for recursive objects. Therefore, we can use Python and Java to help us deal with it. There are several algorithms to generate recursive patterns. One is L system. It contains of three elements: alphabet, the set of symbols the L system is going to use, like a string containing a letter A and B. Axiom, the initial string for the generation, like ABA. Production rule, how each element in the previous string is replaced in the next iteration. For example, A turns to ABA and B turns to BB. Then we can get the second and the third string like this. Another one is IFS system. It is a finite collection of functions that transform a point in the space X to another point in the same space X. It was introduced by Scott in the 2D space. The set code is as follows. Here, X and Y are within -1 to 1, and Fi are linear functions. In this project, I combined these two algorithms by grouping R, theta, and phi as fake alphabet and transform each position by the following function. Comparing to true IFS algorithm, we only deal with one transformation, one more dimension, and the function becomes nonlinear. Then, with Blender's Python API, I implemented my algorithm and make two one-click generating scripts. The first is recursive Sierpinski triangle generator using L system. We could observe clear recursive pyramid when zooming in. It will be extremely tedious to create it in Blender without using such script. The second one is our Mandelbulb generator. Because of the limit of my computer's computing power, I was only able to make 5 iterations. The more iteration it has, the more discrete our Mandelbulb will be. Here are several figures from Daniel's blog. the creator of Mandelbulb. I used his equations, so our results are quite similar. When we zoom in, we could find some resemblance to the 2D Mandelbrot fractals. Besides iterations, the power will also change its shape significantly. Here is an animation. We will increase n from 0.5 to 16. And then from 16 to 5 again. Then we have the result. The higher power it is, the more bulbs. Then is the second part. The Metropolis Hastings is an algorithm to sample according to distributions. Since we learned it in the class, I will go quickly. Below is the set code. A remark is, if we choose transition matrix Q to be the addition of a random number following some standard normal distribution, then the acceptance ratio will reduce, and then we get Metropolis algorithm. We will use it in our code. We want to integrate IR, but observing I2, we can consider it as the expectancy of some square following normal distribution. I implemented 1D, 2D, and 3D samplings in my code. Here we take 2D case for example. You can see both X and Y distribution follows Gaussian distribution quite well. Then we come to integration results. We have 4 interesting findings. First, for all sampling, the time consumption increases by approximately 10 times as we increase iteration number by 10 times. So, the time consumption for each Metropolis sampling should be proportional to the number of iterations. Second, from 1D to 2D, the time consumption increases a lot, but from 2D to 3D, the time consumption doesn't change a lot. However, we do obtain a higher dimensional set of data points. So, comparing to brutal Monte Carlo sampling, Metropolis sampling should be much more efficient to deal with high-dimensional problems. Third, even though for all sampling we obtain the least relative error in the 100,000 iteration cases, the increase of iterations doesn't necessarily secure better iteration results. So, we could see the variance of this integration method is quite large. Fourth, sampling with higher dimensional also doesn't secure better performance. The relative error for different dimensions doesn't differ a lot. Therefore, we have the following results. Metropolis sampling method has an advantage in efficiency for multivariate sampling, but we may consider another integration method after such samplings. Thank you for watching. This is the reference.